Hi, this is Rubaat Khan, and this is lecture 3 of the series. In this lecture, we will see the underlying mechanism of recursion, which will answer the question how to move up the tree automatically. So let's get started. Well, by now you know what a stack is and how it works. We also very well know that functions or methods are of two types, void and return. But not too many of us know that void functions are also return type functions but return nothing. So void functions returns nothing. So let's prove it. So over here I have a simple function named test which simply prints a string. Now let us write the word return at the very last line of the function. And if we run this function, it will work exactly in the same way if we hadn't written return. This means that, or this proves that, void functions also have this return keyword, but returning nothing, empty. This is not some empty string. Do not confuse nothing with empty string. In a void function, you simply write the keyword return followed by nothing. This means that void functions, or this proves that void functions are also of return type functions, but returns nothing. So as void functions return nothing, we do not have to write it. Okay? But it is there, but invisible. We don't have to write it, but it is there. Now it's very important to know that every method call is a push function. Okay? So with every method call, the state of the function is pushed in the RAM stack. Now, what does this state mean? State means the values of variables and addresses of pointers. Okay. And with every return, okay, let's write it over here. So every method call, so whenever this method test is called, the state of the function will be pushed inside this RAM stack, and when the program will see the word return, whether written by you or invisible, it will pop. So every return will pop. Okay. Now let's look at these push and pop on the tree that we're working. So this will give us a very clear idea how things work. Now let us look at this tracing on the paint function on a binary tree. So this is the first method call, and this is pushed in the stack where n is pointing to A. So n is pointing to A. Now let's work accordingly. So the condition is if n is not none, which is true, n is not none, n is a valid node, then we color it red. So we color it red. And then a recursive call paint, and in the argument we are sending n.left. So therefore there will be a push function, or the state will be pushed. So let's point this by an arrow. So this was the first state pushed in the stack. This is the second state pushed in the stack. Now, when n.left is sent in the argument, over here it's received. So n over here, n is pointing at b. So in this state, n is pointing at b. Remember, as we have made a jump from this line is not read yet. Okay. So now we're over here. N is pointing at b. B is not none, which is true. Therefore, we will call it read. And again, another method call. So this is another state being pushed. So we are moving left from n. N at this state is b, so we are moving left of b. So if you look at the diagram, left of b is none. So n is pointing at none. So this if condition is not satisfied as n is none. Therefore, what happens is the program sees this invisible return statement. Okay. If n is not none, this condition is false because n is none. So this if is not executed. We move outside the if condition. This is the outside if condition, and we see return. Even if we don't return, as I mentioned before, there is return invisible. So every return is a pop. So this state will be popped from the stack. And if you remember, the top of the stack now will point to this state. So this line has been executed. Now it's time for this line to be executed for execution. So at this state, n is b, so we are over here. So from b, we are calling the paint function again and moving to n.right. This means that there will be another push of state. So let's put it over here. So let's write it. So over here, again, it will be def paint, and in the argument, as I'm sending n.right, and n is pointing at b, so n.right is also none. And we already know from the code that if n is none, so the if condition was if n was not none, and as if n is none, this if will not be executed, it will see return. So this will also be popped. No, both these lines have been executed, and now it moves outside the if and sees a return. Return means pop, and we go back to this method call or this state inside in the stack. This method is done working, or this line is done working. Now this is the second method call from this state. So n is pointing at a, so n.right means the node marked C. So n is not none, C is definitely a valid node, therefore this if will be executed, so I'll call it read. And then from here again, I'll move left and I'll see a none, and I'll move right, I'll see a none. When both of these lines will be executed, this state will also be popped. Finally, I'm done painting all the nodes of the binary tree. Now, the best part of recursion is, even if you had 1,000 nodes in the binary tree, you do not have to worry with all the nodes. As it's recursion, the same thing will take place on every node. Therefore, if we take a small piece of tree or the smallest piece of tree possible and write our code so that it satisfied this small tree. No matter how long the tree is, your code will work correctly. Okay, this is the beauty of recursion. So in the following lectures, what I'll try to do is I'll try to solve a few problems, okay, on binary trees using recursion. Thank you.